Hello, Houston. We have been talking so far about theories of general knowledge. Last lecture, we were talking about feature comparison or definitional theory, and then we blended from that over into prototype theory and ended up talking about and comparing vertical as opposed to horizontal means of organizing material. Now, we're going to go into another distribution system, and the concentration now is going to be even more on retrieving information. If we can put the information on the screen, we'll start off launching ourselves into what are called semantic network models. The emphasis now is going to be quite different in some ways from what we've been looking at so far. It represents essentially a web of interconnected elements that are thought to exist in our memory, and these intersections are labeled as nodes. So basically, one of the most important concepts we deal with here in the principles governing semantic networks is the concept of a node. And a node is simply defined as an element which represents a concept within a semantic network. So any concept is represented in this theoretically as a node of information. The nodes are linked to other nodes in the network, and thus the network is formed. So you've got node connected to node connected to node, and so forth. And the net result is that the link between them is what is called a labeled relationship. So if we have one node or piece of information linked to another one, the connection between them is considered to be a labeled relationship between them. And those relationships then offer us a number of different organizing bits or strategies for using the information that we've got. One possibility is category membership. A cow, for instance, is a mammal. You and I are primates, as are gorillas and apes, and so forth. Those are examples of category memberships where the category animal is linked to primates and through that to humans, apes, gorillas, and so forth and so on. A second way in which these elaborated relationships can be labeled, relationships can be utilized, is in terms of attributes. So for instance, what we do is one of the attributes of mammalness is warm-bloodedness. So one of the nodes would be warm-blooded, and all the things that are implicated by that, body heat when you touch it, susceptibility to cold, and so forth. But those in turn, linked to the attribute of warm-bloodedness, are labeled relationship to mammal as a concept. So in essence, the two nodes are mammals and warm-blooded, and the link between them is a means by which we can list the attributes of any particular concept. And finally, then, there are a variety of other meaning-based relationships that can be developed using this concept. So the precise form of the network is going to differ from model to model to model, and we're going to look at two or three, probably three different models here today to show you some ways in which these general concepts of node and linkages between them can be utilized in a variety of ways. And then we'll be looking at things like, for instance, reaction time data to show us the efficiency of how we can ask you a question, true, false, and you can search through memory and find the answer if you can link two pieces of information. That's kind of going to be the driving force behind the experiments that we'll be looking at today. So the labeled relationships essentially form memory links among the nodes, and they allow us to connect the nodes meaningfully, to go to one and link to the things that logically relate to it. Alan Collins and Ross Quillian, back in 1969, proposed a hierarchical network of semantic information. And I'm going to show you a demonstration here in a minute that forces us to have this kind of a model, as I'll get to in a minute. What I'm going to do is ask you to look at the screen and we will show you some of the dictates of recall. I'm going to ask you to recall a particular piece of information out of your memory, an effort that you have never been asked to do before, I guarantee you. Okay? And so in this situation, I'm going to ask you to get ready. A word which is about to be pronounced and appear on the screen will appear right here within the brackets. Okay? Have you seen or heard this word before? Left hand up means yes. Right hand up means no. So you're going to have both hands free so you can put one or the other in the air as rapidly as possible when I ask you, have you seen this word before? Are you ready? Masterling. Right hand means no. Left hand means yes. Notice how rapidly the hands went up in the room. Within about, what would you say, 3 or 4 seconds, you had made a decision in looking at and listening to Masterling that you'd never seen it before, and you're correct. But think about that a minute. Your vocabulary, theoretically, when you enter college, is estimated to be in the neighborhood of 50 to 60,000 words. By the time you exit college, your vocabulary is between 100 and 120,000 words. You functionally double your vocabulary one more time during college years. It's the last great increase in vocabulary size that you will experience. And then as you become a professional in whatever your chosen occupation is, you will continue to add to that vocabulary for the rest of your life. But that's a more slow accumulation. So you're kind of in the midst. This being a 3,000 level course, most of you in here are arguably either juniors or seniors. So let's assume that we've got a positive growth curve in terms of vocabulary. If you started with 60,000, given that you're bright, it might be up as much as 90,000 words now, given that you're roughly halfway through, certainly at least 90,000, if the biggest part of the growth is near the beginning of college, when you're in English classes that have vocabulary assignments and so forth. And yes, all of the basic courses. You remember how boring it is to learn basic definitions in Intro Psych, as an example, but it's just in the nature of introductory courses in college. There's a lot of vocabulary to master, because you can't be a psychologist till you can talk like one and talk to one. So the point is that you've got, and I'm essentially trying to document to your satisfaction, that you may arguably have a vocabulary at least 80,000 words now. And you had to perform an exhaustive search of that vocabulary, because for the word masterling, the correct answer, as all of you got, is no. You've never seen or heard that word before. And so in that situation, you had to go through every single one of those 80,000 words before being able to vote yay or nay. Yay, you could vote as soon as you find it. No, you have to do an exhaustive search. Given the speed with which you did so, I think you'd be willing to argue that you cannot process 20,000 words a second and go through all 80,000 to say, no, it's not in there, and then vote, okay, I didn't see it before. What that forces on us is the idea that when you and I go into memory, we have to use a branching system of some sort. We have to know where we're headed. We have to go into a particular place and be able to go there confidently and lop off large amounts of vocabulary that we literally never look at. When we're looking for masterling, we don't go in to verbs. We don't go into the L words. We don't go into the Z words. We go to the M's, and we start looking there. Now the question then is, okay, given that we can respond that rapidly based on an exhaustive search of our memory, how do we scan memory? How do we get to the information we need and we know it's in there? Well, the answer is there are several different theories that have been proposed, a couple of which we're going to show you. But let's examine here the possibility that what we've got is a model for recall that is based on the sound of the words, okay? The sound of the words. Maybe we're searching for recall in that situation, okay? That's one possibility. If that's true, then what we might do in searching for masterling, we're going to look at ling and so forth, looking at the phonemes. So if we go in under sound, one possibility is that we start with So we go down through the great phonemic register, and when we get to M, we then look under the M category and we find a number of different possibilities. Massachusetts, match, maverick, monkey, mother, and a bunch of others. So there are a lot of candidates. The result is we go back in. Under we're now going to look under a. And under a, when we're looking at ma, we find Massachusetts, Match, Maverick as the major ones. There are some others, but those are the major ones. Still haven't found it exclusively and for sure. So we go back in under, in other words, now we're going to look at math. And when we get to the sound, we find that, lo and behold, there are no candidates. Maverick is close, but if you feel your vocal cords, as we talked about it once before in looking at phonemes, the V is vocalized, so your vocal cords vibrate. The F sound in Masterling, your vocal cords do not vibrate when you're doing the sound. So basically, you only have to make 3 decisions to be able to vote confidently and bet lunch money. No, I've not seen or heard that word before. It is not in my vocabulary. If you want to go one further, you can go in under math and look for the t sounds, the words that have cleared so far, yes, 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 but there's nothing there. There's no word anywhere in English that is pronounced maft anything. Mafia is spelled the same, but that's ah. That's not under ah. Mafia is not classed with match and maverick and so forth. So in essence, there is no English word that starts out ma anything. And thus, given that kind of a branching model, that's the kind of, it may not be sound. The likelihood is that that's one of the factors, given the fact that we sometimes draw words that rhyme with each other when we're in the process of constructing a sentence, as we'll examine later on, not in this lecture, but a later one. Sometimes we bring out a word that rhymes, and that is the basis for punning. You know, we're close in the word that we assemble, but it's not right on. Sometimes the effects are funny, sometimes they're embarrassing, but the net effect is it's a retrieval process based on sound. This is the way a model might work if we organize based on sounds. And that would provide us with very quick access to the information. So that basically what I'm suggesting is that we've got to have a hierarchical model of some sort. Because basically what it does is to store anything that applies to all memories of a category at the highest permissible level within the category. Collins and Quillian suggested a model like that when they developed a model that was based on recall of meaning. And if we do this, we might do the following kind of a thing. That is, in this case, what we've done is to store anything that applies to everything in a category under the information, at the highest level in the hierarchy that's being proposed there. The advantage is that it's an efficiency move, because whatever that piece of information is doesn't then have to be stored. The fact that animals have skin doesn't have to be stored with birds and fish and four-legged animals and so forth. So it's most efficient to store skin as a concept with animal, as it is with things like breathing, eating, and the ability to move around. That is mobility. All of those are features of animals and everything under the animal category. Okay? Whatever's known about items at a higher level in the hierarchy is assumed to apply to all of the organisms or all of the elements, the concepts that are lower in that hierarchy, or else they wouldn't be in that hierarchy. That is, if you don't have skin and breathe and move around and eat, you're not an animal. Okay? So those are features that apply specifically to animals. And although the data is correlational that I'm going to show you here in a minute, some rather powerful consistencies develop in how people respond to simple semantic assertions. I'm going to give you some examples here in a minute where you're shown a sentence and you have to react, is that true, is it false? And it requires a search of a hierarchy in order to determine what the correct answer is. Or, what I should say is, if it requires a search of a hierarchy where information is filed, as for instance in the model that I'm proposing here from Collins and Quillian, then in fact we can make some predictions about reaction time. Okay? And so what I'm proposing here, and I'm going to move away from this model, but I wanted to show you some of the features of the way in which it can be organized. So that if we have animals as one category, and obviously I've given you only a sample here of the total information we have, but some of those animals can be categorized as birds. And birds have a rather unique feature. First of all, they have wings, which the rest of us don't have. Did you ever try to fly as a kid using a bath towel? It's a long fall from the roof when you try to do that. The arms just don't work as wings. So birds have wings. Because they have wings, in general, we can infer that they also have feathers. And then because of those two attributes, they can fly. But those features are not related to snakes or fish or primates. Okay? The birds are a subcategory. for which those three features all apply. And in fact, if you then get down to canary, one clear example of a bird, there are actually only two features of a canary that make it a canary. It's yellow and it can sing. Every other feature that we can mention about a canary, it has feathers, it can fly, is applicable more generally either to other birds or to other animals. Okay? And so basically what I'm arguing here is what Collins and Quillian argued is that whatever attribute is filed with a given concept is really true of anything, any concept filed under that category. All right? If you look then at fish as the other example on screen there, fish have unique characteristics at the same level as birds do. But fish, for example, have fins. They don't have wings. They can swim, which birds may or may not be able to do, and they have gills. Okay? So those are features that are uniquely true of fish that differentiate them from birds. And in turn, when we look then at fish, I've given you just a couple of examples, like a salmon, which is pink, is edible, and swims upstream to lay eggs. There are other animals that are pink, there are other fish that are edible, and there are other fish that swim upstream to lay eggs. But those are three primary features of salmon. Contrast that with a shark. Because a shark, one of the major features, a salmon can bite you, but it's not going to shred off a leg if it does so. It may nip you, it may bite you, but it's not biting. It's not the major thing that we think of when we think about salmon. So biting is an attribute of sharkness, the fact that it's dangerous, and you could also file some other things. Are you aware, for instance, that sharks never sleep? They move constantly because breathing through their gills, they have to keep water and thus the oxygen within the water flowing through the system constantly. So that's another feature I didn't have room to put on there. But that's another one we could list about sharks that's uniquely true in that package of sharks as a whole. So what we're going to do now is create essentially a sentence true-false reaction time study. Okay? So I'm going to take a sentence like a canary is a canary, which is a kind of a semantic tautology, and ask you to react on a computer. That is, if you were a participant in Collins and Quillian's original research, you'd be looking at things popping up on the screen, and you'd have two buttons. You press true or you press false. And what's plotted here are only the reaction times where the actual correct answer is true. There was one other thing I meant to point out to you before I move past this, and that is that in terms of that model, there are three different organizational features that are true throughout. One of them is the idea that we have in this model what are called units. Okay? A unit is basically words that represent one thing or subject or concept. Okay? And there are several examples there. Canary is a unit. Bird, for that matter, is a unit. But it's a more generalized organizational concept which has components, other units that relate to it. The second thing that's illustrated there is properties. Properties are essentially the characteristics of the unit. So when we look at any given word on the screen there, the line connected to it to its right is essentially a listing of the properties. It's identifying a property of the object to the left from which those lines spread. And thirdly then, we have pointers, which are basically associations among the units and the properties. I misspoke there. The properties are actually the middle unit. I was too busy jumping ahead of where I was trying to be. The properties are the words, the phrases that are listed there. So we said a bird has wings, can fly, and has feathers. Those are the properties. And the link, the arrow connecting between bird and those properties, is what is referred to as a pointer. It indicates an association of unit that relates to a feature or properties that link the, let me say it again. Those are the links between the unit and the properties, are the pointers. And what we're going to predict then is that sentences will take longer to process as they involve 1, 2, or 3 levels of processing. It's one thing to say a canary is a canary. You don't even have to go into the model to be able to answer that. Okay? But if we ask you a canary is a bird, you've now got to go to bird and then link to canary before you can answer true. So that would be a single, a 1 unit leap in processing. You have to go from the second level to the third level in that model, 1 unit difference. If we were to give you a statement like canary is an animal, now you've got to jump across 2 levels. The link unit size is 2, and so forth. So we're going to argue that the further apart the pieces of information are in the model, the longer it's going to take you to answer true when the statements are true. So again, this is an equal mix of true and false statements. If we compare only the reaction times, plot only the reaction times for true statements, the data that you get looks something like the following. And essentially what we're going to argue then is the judgment of true-false takes longer the more levels that are involved in the assertion. And so we plot it this way. On the left side is a measure of reaction time in seconds. And on the bottom, on the x-axis, is the distance of the relationship between the two units that you're trying to indicate are true or false. Is there or is there not an equality or a linkage between them? And so when we do something like a canary is a canary, it takes just about a second to react true to that. That is true. That's, as I said, a kind of a semantic tautology. It's an absolute true statement. A canary is a bird. Look at the addition in reaction time. It's about 25% longer, at least 20%, because now you're up to about 1.2 seconds before you can confirm statements like a canary is a bird, because you've got to link across two categories in accord with this model. And thirdly, then, a canary is an animal takes just slightly longer, because in this case you've got to link from canary to bird and from bird to animal. So you've got to link across two categories in terms of the distance between the relationships that you're comparing, and the reaction time is longer. The data is even more impressive if we look down a little bit further. And that is, in this situation, we notice, first of all, that we have a more rapid reaction time for questions that involve the superordinate relationships, canariness, birdness, and animalness. Those are the superordinate features in this particular situation. Notice also that there's a more rapid reaction time at both levels as related to the same versus more distant levels of relationship of attributes. And by that, what I mean is, look at the difference in this line. Because now what we've done is to go to a particular category, and then we have to review the features of that category. So basically, to make a simple statement like a canary can sing, you have to reach into animals, through birds to canary, and then you have to review the very limited, unique features of canary. That actually takes longer than making the link between a canary is a bird is an animal. So a true-false reaction time to a canary is an animal is about 1.25 seconds. A true-false reaction time on average to statements like a canary has a feature involves singing takes about 1.3 seconds. You've got to search into and find canary, and just a little bit longer to review the attributes that are related to it. And if you have to jump across, a canary can fly, you've added yet another level of complexity, because now in this situation, animal to bird to canary, linking back to bird as a feature of birds. That takes about 1.4 seconds. And it takes fully a second and a half, 33% increase in processing time, going from a canary is a canary to a canary has skin. Because in answering the last statement true, you have to go from animals to birds to canary and then back up to animals and review the many features that describe uniquely an animal. And does canary have that? So the answer ultimately is yes, but look at the difference in reaction time. This is strictly correlational data. Okay? It doesn't mean absolutely that is the way the words are organized. This is correlational. But there is a very impressive array of correlations that you have in this situation, given the assumption that the information is organized hierarchically, as Collins and Quillian suggest. Let's use that same data and show you a problem. In fact, there are two of them with this particular situation. One of the problems is that it takes longer to verify that a chimpanzee is a primate than it does to verify a chimpanzee is an animal. Okay? I've removed the times because I don't know the exact reaction times for this. But for an animal, a statement like a chimp is a chimp, we found what that rough relationship was. A chimp is an animal is up about here. But if you think about it, that's actually two levels removed, because a chimp is a primate is an animal. And yet the average reaction time, if you look at a chimp as a primate, is this way. That is not consistent with the model. That kind of a glitch in our correlational data causes problems. It suggests that just simply categorizing it by information is not enough. Because we would have expected, given the relationship between the left and the rightmost true-false statement, that the middle one would be somewhere between them in terms of reaction time if the model is strictly correct. Now, what it's probably thrown in there is the issue of something like frequency. The more rapidly we use, the more frequently we use a word, the more immediately we can access it. And you and I don't tend to go around talking about chimps being primates. We're more likely to talk about a chimp as an animal and the treatment that it gets, good, bad, or indifferent, and so forth. The second problem is that this data cannot account for what we described earlier as the typicality effect. More typical members of a category are easier to identify than less typical members. Okay? It would take longer, theoretically, if I were to give you something like an ostrich has skin than it would to confirm a canary has skin. It's easier to verify that a canary is a bird than it is to verify that an ostrich is a bird. Same general issue. Both are at one level from birdness. But there's a significant difference in the reaction times. That would not be predicted by this model. The reaction times theoretically should be the same. This in turn led to the creation of a different kind of model. And in this case, what we're now going to do is to look at what is called a spreading activation model, which Collins and Loftus proposed several years after the original Collins and Quillian work. Spreading activation emphasizes the concepts are joined by links, as we showed you earlier, that show relationships between concepts, where the concepts are the key element there. And in this particular situation, we're going to show you a kind of a network that is proposed by Collins and Loftus. If we start with a basic concept like red, just to give you an example in this particular situation, we're going to show you just a very small part of the information that you have organized around the color red. Okay? It differs from the hierarchical model network, the hierarchical network model, in that the length of each link represents the degree of semantic relationship. Okay? So red is pretty tightly related to colors. Okay? Red is closely related to other colors. That link is a very short one. And it's even arguing, in this model, that red is most directly related to orange or green, red and green being linked so much at the Christmas season as one example. That those links are closer to red than is a color like yellow, which, is part of the spectrum and sometimes is mentioned with yellow, but we don't tend to wear red and yellow together. So they don't tend to be as tightly related to each other semantically. So the length of the unit of the connector is a measure of the semantic tightness or the closeness in relationship between individual words. This model accounts for the typicality effect because the links represent the tightness of that semantic relatedness. Car and bus are obviously closely related to vehicle. So if we had a whole concept of things related to the color red mediated through something like fire engine, which, yes, is red, but fire engine itself has a whole package of information and meanings that it itself is related to. Okay? And so what we find here is that there are several predictions that we can make out of it when we look at this particular thing. For instance, car and bus are closely related to vehicle, more so than the less typical fire engine and ambulance, which will not activate the vehicle concept as rapidly as car or bus. So if this is a reflection of the meaning that you carry around with respect to these things, what we're arguing is that if car or bus becomes the topic, it activates the concept of vehicle much more directly than does something like fire engine, because the immediate associations to fire engine are things like it's a truck, people ride on it, it tends to be in the neighborhood when there is a fire, and so forth. Those are the things we tend to think of, rather than, it moves on wheels like a bus. That's a mediator, but it isn't the thing that is immediately activated when you think of something like fire engine. So in essence, as you look at the model there, you see that both ambulance and fire engine tend to be fairly tightly related to each other. If you think of one, you tend to think of the other. If we have an accident, both types of vehicles tend to be there. They both mediate to vehicle, but not as directly as to each other. When you think of fire engine, you think of an ambulance, and vice versa. We had a transformer blow in our neighborhood last week, shut down about 100 square blocks. We ended up with something like 11 fire engines and 2 ambulances. The ambulances, it turns out, were not needed because nobody was hurt, but it was a typical emergency situation. A whole bunch of sirens, and the mediator there, in fact, I don't even have it on there, would be siren, but siren would probably fall halfway between ambulance and fire engine and be even more tightly linked to that than either of those is to truck, which is a more remote association, but it's common to both of them. But look at the contrast. Look at vehicle. They are, yes, related to ambulance and fire engine, but look at how much greater the distance is, suggesting that the linkage is a much more remote one in that particular situation. And we can add some other concepts here. For instance, with fire engine, we also then tend to think of fire, which is directly mediated to red and also to fire engine. And in turn, fire and fire engine tend to be related to house, which is one of the first things we tend to think of when you mention fire and fire engine. House is a very immediately related concept there. House has some other things that are related to it, which we won't go into. Let's go back to red and look at the fact that red also relates to apples. Not necessarily the first association you have to it. And in fact, one of the things that is implied here that I'm not going to talk about is that certain concepts like apples may call red much more quickly to mind than red calls apples to mind. So there may be a difference in the unidirectional travel in this semantic network under certain kinds of conditions. Okay? But car and truck are certainly closely related to vehicle, more so than apples is directly related to red. And the spreading activation model assumes that when a concept is processed, activation spreads outward from whatever concept you're dealing with along the paths of a network such as what is diagrammed here. Okay? But efficiency tends to decrease as you travel further outward. The example being fire and house. We may not, in considering red, we may eventually link to fire, and in turn that kicks in with house and so forth. But the linkages, the more remote one concept is from another in this map, the lower the likelihood that when you think of the central concept, in this case red, you're immediately going to think of street. And yet it doesn't take too many words to get from red to street. Red to fire engine to street is a fairly direct link, although semantically each is not very closely linked to the other one. So the effects decrease over use. All right. So when we start adding some rather remote concepts, red could also be thought of in terms of sunrises and sunsets, and in turn those link to clouds, because oftentimes the effects that we get with sunrises and sunsets are caused by clouds. So you sometimes tend to think of, couldn't see the sunrise because it was cloudy, or did you see this morning's spectacular sunrise with the reds, the yellows, and whatever. And finally then, another concept like roses, certainly at some level is also related to red, and we don't tend to think of that immediately very often, but when we think of roses, we also mediate to things like flowers and violets and a whole other set of things that we could connect in that way. So that when red is activated, it should strongly activate things like orange and fire, but less so things like sunsets and the various elements that may occur in this situation, like roses, for instance. Okay? Which in turn then leads rather interestingly to another issue, and that is, could we prime some of these links? Could we set people up to be more likely to think of particular kind of things? Well, it turns out the answer is yes. And the way this was demonstrated is rather interesting. That is, we're going to look at spreading activation and do it in terms of the issues that I've just talked about. The decline in activation, the further out or more remote a concept is, the decrease in effects that you get, the more remote those concepts are. And thirdly, the fact that decrease in effects can be due to disuse if you don't think of it very often. That kind of distances the concept in that model as we were looking at it. Or other activity. If you're more frequently related to, if you are a fireman, they just announced the addition of some number of policemen to Houston's police force today. If it had been firemen today, we might have been thinking in the context of firemen, fire engines, and so forth, and the color red might have been primed, but what would be featured there would be the link between red and the various features related to fire. And then we also have the declining effect of distance stimulation. The more remote the link between whatever we're thinking about now and any tangentially or distantly related concept, the less the effect is to strengthen that. The longer distances are not as strengthened by a central concept that has been activated. Let's test it in the following way. Using semantic priming, I'm going to define that essentially as an effect of prior processing, I should say the effect of prior processing of related information on processing time for a concept. That is, if you've thought about something in the network we looked at a minute ago, does that increase or decrease the length of time to get from the one word to the other one in the network? And what we're saying is that priming decreases that time. It alters it. Okay? How does the model work? Well, it was tested in a rather interesting way. What I'm going to do is to ask you again to use your left and your right hand in the following way. Meyer and Schwanevelt asked subjects to judge whether letter strings were or were not words. So I'm going to show you a series of letter strings, and in each case have both hands on the desk and tap in the following way. Left hand means yes. See, I'm not going to confuse you and make it be no this time. Left means yes. Right hand means no, it is not a word. Okay? And I'm going to go through pairs of letter strings down the screen. So the first one will be just about under the hand, a little further down on the screen there. Ready? React with a tap of the hand, and you can do it at home too. Just because you're alone doesn't mean you can't do that. The following. Oh, the other hand. Right hand means no. So everything's there. Ready? This is supposed to be a reaction time study, folks. Word appears, react. Okay? The answer was yes in that situation if you were confused. Ready? That's better. Ready? I messed that up. Ready? 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 Now, what we've looked at, words that differ in several different ways. Okay, I'm sorry I messed up one of them, but what theoretically was demonstrated here is the following. The words and what's actually important here is this is the setup word. This is the stimulus in the situation on the left side, and it's being used to prime you for whatever may be following, and it may or may not prime you. So there are various kinds of relationships that are reflected here, okay? These two are examples of where the word on the left is followed by, yes, a string of letters, but it's not a word. It's just a nonsense string. Yes, it's letters and recognizable as such, but it's not a word. That's one, and in the entire list, there were pairs that were that way. The one word on the left had no relationship at all to the one on the right, and it was in fact a string of letters, kind of nonsense syllables, essentially. The second situation was this, where in fact the word on the right related very directly to the word on the left. When you think of apple, applesauce is a very obvious connection, and table chair is the highest word association link in the entire human vocabulary for English. It elicits that with the shortest reaction time and the greatest surety. So those, in that case, we would expect to see priming. We would expect to see shorter reaction time when you hit that second word. So what we're going to be plotting here when we look at it is the average reaction time for each of the pairs of words. I've got two illustrations of each concept here. And the third one is situations like this, where yes, both of the words, the stimulus and the response, or the second stimulus, are words, but there's no known link that I could think of between hammer and doctor and jelly and onion, with the possible exception that both of them are foods. I didn't think of that. I shouldn't have had it there. When I retape, I'll change that next time. But those are the three different relationships that are reflected in that particular situation. And in essence, the results were very clearly documenting the effect that we were looking for. And that is that reaction time priming effect was clearly demonstrated. The reaction time, comparing time to correctly identify when the second string was a word, the second word was judged significantly faster when it was semantically related to its predecessor than when it was not. Okay? So in essence, what we're seeing there is that the reaction time for sauce and chair, where the relationship was there across the various elements of the longer list, those reaction times were markedly shorter than were the reaction times for unrelated words, where, yeah, the stimulus and the response is a word, but this doesn't relate semantically at all. And so basically what was demonstrated is exactly the priming effect that was expected. And then they even tried it in a slightly different way. Okay? Now, having defined it, let's also look at another model, which basically is going to go back to the basic model that we were talking about before here, and look at a related prediction. Another group of investigators, McNamara, he and the family, I guess, were looking at this in the following situation. If we prime bread, we can decrease reaction time for solving a problem with butter, because bread and butter tend to be fairly close semantic relations to one another. You think of bread, butter is one of the first associations you tend to think, and that link between bread and butter is a tight one. They are semantically close to each other. Does priming with bread decrease reaction time for solving a problem with popcorn, which is related remotely through bread to butter? Okay? The link between butter and popcorn is not as direct a one, and it would be confounded with our associations with bread. But the answer is essentially yes. Okay? That is that the reaction time where if we'd done this in the original experiment, the reaction time there was that priming with bread will elicit a shorter reaction time for butter than it will for popcorn, because there's a mediator. There is a link, but it takes longer to get there, and so the priming effect does work in that situation. The model is based then on semantic relations that directly represent by links the various concepts that are depicted there. But it also provides a basis for doing feature comparisons, as that theory was discussed earlier, as we looked at it earlier in the lecture. Spreading activation model includes assumptions about things like the semantic hierarchy model and also the feature comparison models, both of which we have already looked at. So the hierarchy model had to do with word order of association and so forth, and the feature comparison model was, what things do you think of when you think of a bird? And you'll see that these are different attempts to explain basically the same things. And in deciding that a mallard is a duck, we can do that according to the theories we've already reviewed in a couple of different ways. Okay? We can find superordinate links between mallard and duck, and also between duck and bird. Each is linked to the next in that table that we laid out on in the lecture last time. We can find superordinate links between mallard and duck, and between duck and bird. Or we can find common properties in the concept of mallard and the concept of duck. In other words, we can just do a linkage through the kind of theory that we're looking at here. There is a possible problem here. That is, with the spreading activation theory, we've got a very interesting problem that shows up. And that is that as any theoretical model gains in flexibility, what it tends to do is to lose predictive rigor. And what that does is to diminish its ability to generate heuristic predictions. So as we refine the model to explain the data that we've found, we then begin to lose rigor. We lose predictive rigor. Making too many assumptions, some have argued, actually reduces the fruitfulness of the predictions that one might generate out of a model. The experimental jury relative to the spreading activation model is still out on that, but it did lead to a very interesting alteration of that called an ACT model, which is essentially adaptive control of thought. All right? In this case, this was developed by John R. Anderson, and will be the subject of quite a series of studies running over a decade or more. What he's arguing essentially is that knowledge is represented in semantic memory as a series of interconnected propositions, slightly different word for the connectors that we had earlier. And he's arguing essentially that we have then a propositional network. So we're going to define proposition in this case essentially as the smallest unit of knowledge that can be judged true or false. Okay? A bird has wings is a fairly small unit. It's not a great intellectual leap in terms of this theory. And what he's going to argue then is that semantic knowledge is stored in an interconnected network of such nodes. And the activation essentially spreads along paths from node to node. And they're active to new nodes along paths connected to the originally active node. So the activity starts at a node and spreads outward along the pathways to other related nodes, is the model that we're working with here. This one is then going to argue that we retrieve stored knowledge in the following way. Okay? The issue is going to be, how do we retrieve stored knowledge? And the study that was done here is a bit of a complex one, so I'm going to describe it to you in a couple of different ways. But in essence, what we've got is the following situation. subjects are going to be read in the experiment that is essentially derived to confirm this particular approach. They're going to be read 26 sentences of the kind, a person is in the location. And what we're going to manipulate here is the people that are in the sentences that are read and also the locations where they are positioned. So what we've got actually in this situation is the following kind of a model. Given a sentence like a person is in the location, we're going to vary two things. So we've got a 3x3 situation here. First of all, we're going to vary the times a person appears. So this might be labeled not person, but times of appearance. How many times is a given person going to appear in this cluster of 26 sentences? Okay? The second thing that's going to be manipulated is in how many locations does a given person appear? And to relay this, I mean, it seems straight enough this way, but to really confuse things, what the authors did was to generate a number system that looks essentially like this. What they're arguing is they're going to give you a two-digit number or a pair of numbers, and what that reflects is, first, in the test sentences that you're going to be given afterwards, they're going to read you a sentence such as, a hippie is in the park. So hippie is the person, park is the location. And what we know about the experiment is that hippie may have actually been used in 1 or 2 or 3 of the 26 sentences that you heard. Okay? So that variable is handled in the initial reading of 26 sentences, which are read, which you read before you start the experiment. So you just literally read, a hippie is in the park, and so forth, 26 times. And you may have hippie shown only once, he may actually occur twice, she may be in there 3 times. That's one variable. The second variable across those 26 sentences is, how many times is the location mentioned? And the word, if the original sentence was a hippie is in the park, it may be only used once. The word park may actually occur in one of those 26 sentences. Alternatively, it may appear 2 or 3 times. So essentially, we're going to manipulate how many times the person appears and how many times the location appears to do it relationally correctly for you. And so what happens is they are read this first. A person is in the location, and the particular person, individual, occurs 1, 2, or 3 sentences. Secondly, the particular location occurs in 1, 2, or 3 sentences. I'm re-saying it to make sure you understand. And then the subject is going to be shown a specific sentence and asked to respond. So, for instance, in this particular experiment, you might be given a 1-2 sentence, such as, a debutante is in the bank. How many times is bank used in the total list of 26 sentences? Twice. That's why I spent time showing you the model. The 1-2 to the left, which is there for the experimenter's benefit, not for the subject's benefit, tells the reader that that's a sentence that involves debutante, which is only used 1 time in those 26 sentences, and the debutante is in a location which is actually mentioned twice in the list of 26 sentences. Okay? Alternatively, you may get a sample sentence is something like that. A hippie is in the park, a debutante is in the bank. Those are 2 different possibilities of sentences that appear among the 26. Okay? False test sentences include things like, a captain is in the park. That's false. And in fact, in that one, we know that captain appears 3 different times, and park is also used in 3 different sentences. Once, maybe, with a captain in the park. It turns out the answer to that particular one is no. But essentially, you have sample sentences like, a hippie is in the park, a debutante is in the bank, and then you have some false statements such as, a hippie is in the cave, a captain is in the bank. Those 2, when they pop up on the screen as a true-false test, should elicit a false response. And what we're measuring then is reaction times when the test sentences appear. So the test sentences have exactly the same structure as did each of the sentences that were in those 26 that were read. And what we're looking at then, as you can probably predict, is, if you think back to the network model we were talking about before, if you've seen the word hippie appear several times, you develop a concept there. Probably the maximally beneficial situation is where hippie, excuse me, is used 3 different times, but no, that won't work. Scratch that. Let me go back to what I was basically going to be saying here. We're going to look specifically at reaction time, okay? And what was found was that reaction time increased as a function of the number of links to each person or location mode in the network. That is, it didn't matter whether it was person or location. The more links between the one and the other, the slower the reaction time was. A 1-1 sentence, like a lawyer is in the cave, which is the example I started to get into, has one individual who appears only once and in only one location, which location is never mentioned any other time. No other actor in this series of 26 sentences is ever mentioned as being in a cave. All right? And so basically, the reaction time for a sentence like a lawyer is in the cave, which is a 1-1 sentence, meaning it did occur, well, I'm not going to repeat it. That's the fastest reaction time you'll find, because you've got an actor who is only mentioned once in one context. That is the fastest reaction time. If you have some poor guy, some poor gal, who has been mentioned 3 times across and in 3 different locations, that is the slowest reaction time. So the conclusion there is, when we look at the reaction time itself, that there are several things that we can conclude from it relative to this network model. The first thing is, basically, that the rate of spread of activation from each of the 2 concepts can be analyzed. Secondly, the length of the path joining the 2 concepts can be analyzed. And thirdly, possible alternative paths that the activation might find can be verified. But the time to verify is related to all 3 of those. The time to get a true or a false out of a particular statement is related to the rate of spread of activation. Secondly, the length of the path joining 2 concepts. And thirdly, possible different ways to get from point A to point B. So a 3-3 sentence was much slower in being correctly identified because each concept is linked to 3 other concepts. So you have a much greater complex relationship or network between the 2 concepts. So even though they've appeared more often, because they've appeared in so many different contexts, you've developed a lot of different network connections from that person to that situation. Okay? And so a 3-3 sentence was much more slowly identified because there were so many different links to the 3 other concepts. Hippie to 3 locations and park to 3 locations, to 3 people, I should say. So you've got a much more complex network there. But finding it is delayed by the number of links that are in there, the slowing of activation effect. The further the link has to go because it's diluted across 3 different paths. You could think of it as a kind of a certain amount of energy for activation. And when you go to a concept like debutante that appears in only one situation, that energy goes specifically to the concept of where she was located. But if a concept like hippie appears in 3 different locations, that energy dilutes. It takes longer to travel from the one to the related concept to answer it particularly. That leads to the proposal of what's called the fan effect. Okay? And we define the fan effect essentially as the increased time to verify a link caused by increasing the number of links to a specific concept. So this is something derived out of the work attempting to confirm frequency of use as an impactor of the complexity of the model that we end up with here. Now there's a problem. All of the models end up generating problems in one way or another. But the problem we have here is, and if you think about it a minute, this problem is incredibly obvious, and that is, what this implies is that adding knowledge about any subject, that is becoming an expert about any subject, would increase your reaction time in talking about anything the more you know about it. Because what you're doing is taking the individual concept and you're learning this about it and this about it and something else about it. And this model is then going to predict that the more links you have to that particular central concept, the longer it's going to take you to retrieve the information you need when you're talking about that concept. This led to some additional modification, as we'll see here in a minute. Smith, Adams, and Shore did a very clever study that's going to involve what is called the ACT-STAR model. And it implies essentially that adding knowledge about any subject that is becoming an expert should really increase, should not increase your reaction time. I mean, that's against common sense. We know that. So what Smith, Adams, and Shore tried to do was to propose the following kind of a model. They had developed the concept of a subnode, okay, in this model. And in essence, we're going to define a subnode essentially as a node that links or that is related, that links related ideas in a semantic network. A subnode. We've already defined a node as a center point. We're going to define a subnode as an organizing feature that links related ideas in a particular semantic network. Okay? And so in essence, we start with a concept like ship christening. Okay? We know, for instance, participants in this experiment were given a statement such as, they were given 2 or 3 facts about a given person. Mary is the person we're going to deal with here. One of the things we learn about Mary is Mary broke the bottle. Okay, so we've got Mary in this particular situation. We've got the fact that Mary broke a bottle in this situation. We also know that Mary did not delay her trip. That's the second statement that is given about Mary. So in this context, 2 things have been told to us. Mary broke the bottle, which is ambiguous, although it implies certain things. And secondly, she did not delay her trip. Okay? And then either of 2 statements was also given. Either the third statement was Mary christened the ship, or Mary spoke to the crowd. I didn't have time to model that in there, so you're just going to have to imagine that it's over in the bottom right. But that was the third additional statement that was given. Mary spoke to the crowd is ambiguous. Mary christened the ship clearly clarifies why the bottle was broken. And also the fact that if she was going on that ship, christening it was a very good way to get the trip started. Okay? So essentially, in that situation, the fact that Mary christened the ship is the integrating statement. That puts together the idea that she didn't delay her trip and that she broke a bottle. That's an integrating statement which lends logic to this particular situation, and it reinforces the various nodes that are there. Now the point here is not even so much what I've already talked about and the way that is demonstrated in terms of reaction time, but rather the idea that with 3 unrelated facts, the participants took longer to confirm any one of them is true when they were just hit with Mary christened the ship than they were if, let me back up, Mary spoke to the crowd. It took longer to confirm that is correct when it was part of 3 sentences that don't relate to each other. But when the third sentence was the integrating Mary christened the ship, then they could more rapidly confirm Mary spoke to the crowd is not true. Mary broke the bottle is true, and so forth, because it fits with christening, breaking the bottle, Mary, and not delaying her trip. That becomes a tight package. The subnodes are what we're interested in here, and this is an example of a subnode right here. It has to do specifically with ship christening and the christening of the ship, the actual act of doing so. This is a general procedure. This is the act. The didn't delay the trip is a feature related to this story relating to Mary, and so forth. But the point here is the addition of this model, of this feature, is the following. If we were to give you additional information, okay, for instance, the fact that Jim is also present in the christening, this doesn't foul us up at all, okay? It's simply ancillary information, and we have to search for things related to christening the ship. The addition of that ancillary material, which might in the original model have had present and Jim both relating to Mary, it's on the side. It's there, but we don't have to go through it to get to the other information. The subnodes allow the relevant information to be linked correctly or centrally to the organizing scheme in this situation, which is ship christening. Okay? We can even add other information. For instance, the fact that Mary painted her house. We know that about Mary. And in fact, we could even, from the painting of the house, lead to other issues that are even more tangential to what we're really talking about here. For instance, what color was it? Did she use oil-based? Was it water-based? And so forth. Doesn't matter in terms of reaction time. That is, what the addition of the star feature in the act star model does is basically to add the concept of subnodes. Okay? And so we note the reduction in the number of links that is actually constituted in this particular model. There is a fewer number of links to the central concepts, although they're still linked. You can get from one to the other. Okay? Which leads to some rather interesting predictions, and that is that, for instance, Anderson has predicted that actual recall of a fact may not be necessary. If a fact is judged as consistent with the other information, the very idea that we tell you that Mary christened the ship implies that a bottle has been broken and that Mary was the agent that did it. But we don't really have to mention that specifically. And yet if I describe to you, our common friend Mary christened a ship, if we later learn, you hear from somebody else, Mary broke a bottle, you've got an explanation for that immediately, because you go back to the fact Mary and the ship christening, and bottle breaking is very much an integrated part of that, but you don't have to, from Mary to christening the ship, you don't have to go through the information related to breaking the bottle. And so the statement that Mary broke a bottle is consistent with ship christening and would not necessarily force us to recall the entire ship christening episode or node of linked subnodes. And it would not be impacted by adding many more nodes to the information. We might have a lot of other information about Mary. She's redheaded, she's 5 feet, she's a junior at the U of H, and so forth and so on. That doesn't impact the reaction time to judge Mary christened the ship as true or false. Second prediction by Atkinson in terms of the ACT star model, which is what this newer subnode model is referred to as, is that if you said additional information about Mary painted her house, that fact created another subnode of information, but it only slightly delays decisions regarding the ship christening. I'm restating in a slightly different way what I've already told you. And that is additional facts that we add to Mary's household painting do not further delay decisions. The very idea that we've added the fact that Mary painted her house creates a subnode that you can then pack the other information about. Gee, I wonder what color it is. It's rained a lot. I wonder when they got it done. Did she use oil base and so forth? Yeah, it's all related to Mary, but it does not foul up our processing time related to Mary and christening the ship and breaking the bottle. So we conclude out of all this work that the addition of the subnode concept expands the data and the situations that the ACT star model can actually explain relative to the original ACT model. By adding the concept of subnodes, we've increased our accuracy in explaining reaction time data. Okay? Basic assumptions of ACT remain the same. That is, that activation spreads along paths in a semantic network. Activate a concept, the information spreads outward. That concept is still there. The difference is that the activation is stopped when it gets to an irrelevant subnode. It doesn't continue because it knows it's not relevant to the situation that's being explained there. Let's look at one other major category here, which is a slightly different way of looking at the storage of information. And in essence, the last area that I'm going to cover here is the idea of schema. We're not going to cover this in great detail because the Matlin text, our course text, does a good job with it. But there are some comments that I wanted to offer to make some parallels, draw some connections that she doesn't. Semantic networks are good at the word and the concept level. They're very effective at that level. But they falter when it comes time to integrate large blocks of knowledge. That's where they have greater difficulty. An older theory is much better at that and also more fully developed for depicting clusters of knowledge, that is, great packages of information. Example, think about all the knowledge you have about building location and department location here at the University of Houston. Given that you're mostly juniors and seniors, that is a very complex set of knowledge that you have because you've walked the various paths time and time again all around. That's an example of a cluster of knowledge. I'm going to reach back here to a concept called the schema, which we define essentially as a cluster of knowledge that represents a general procedure or maybe an object or a precept or an event or a sequence of events or even a social situation. That's a definition that was proposed by Thorndike back in 1984. Psychologists in the U.S. in the 1930s to the 1960s were wrapped in detail-oriented SR theories. Behaviorism was the rage from the mid-1930s through the 1960s. And because of that, we got very wrapped up in those detail-oriented theories, and that's all. Meanwhile, in Europe, Bartlett in England and Piaget in Switzerland were focused on large units of knowledge organized into what they called schemas. That is, the research over there was going in a very different direction, and it had almost no impact on our work in the U.S. Schema theory offers an explanation for how knowledge is represented and how that representation facilitates various uses of the knowledge using a different mechanism. Okay? The schema are used, for instance, to interpret incoming sensory data. They can be used to retrieve information from memory, that is, as a vehicle for organization and retrieval. And we can also use it to organize the particular actions that we have learned, or for that matter, to solve problems. The work was published by Bartlett originally in 1932 in a book called Remembering. Okay? One of the most compelling demonstrations in Bartlett's original book was one that featured the following kind of a demonstration. Okay? Subjects were given a series of 3x5 cards that had on them line drawings such as you see here. So there were two circles connected with a line that was just above the midpoint between the circles if you were to extend it. There was a thing that looked like I don't know what you'd call it, maybe a metal link, a chain link that hasn't been closed yet. The Roman numeral X, a thing that's a kind of an upside down diamond with a line in it, a circle with various lines radiating out of it, and a triangle superimposed on a square, not all of which you can see, with a stick coming out of it, or a shaft of some sort. They studied this in the experiment as long as need be. It was one of those low-pressure 1930s experiments. Basically, you were given the card, you were allowed to look at it as long as necessary, and then you put it under your seat. I don't know where you put it, but you put it out of sight, and then tried to draw the image. And you did that until the researchers were satisfied that you could accurately reproduce each of the images. Okay, so they just watched. You studied the card with the two circles and the connector line, put it away, and then drew an image. Researcher took it, gave you back the card, and you could study it again, and then try to reproduce it. So it was a study task kind of situation until the drawings that you were doing replicated the drawings that you had been handed to the satisfaction of the experimenters. That's a little difficult to document quantitatively in terms of degree of similarity, but let's take them at their word. You studied it. A week later, you're brought back, okay? And you're given a recall test. To help you, said the researchers, we will give you a verbal cue. Group 1 in the recall test was given a verbal list. And so they had a list in front of them of words. What am I supposed to draw? The word clue had a direct impact on what the subjects actually drew. So the act of withdrawing, or retrieving, I should say, the information with a particular verbal cue altered the way the drawing itself looked. And so a typical drawing is what's depicted on the left here in the green column. For these double circles with the connector line, in this case, they were given a name like pince-nez glasses, the kind that FDR, Franklin Delano Roosevelt wore, the kind that perch on your nose. That was the recall cue, pince-nez glasses. Give me the stimulus that looked kind of like a number 2. Well, in fact, that's the kind of diagram you get as a recall item. How about the thing that looked like an hourglass? Well, that's a pretty good cue, but look at what happens to the drawing. The middle's not connected at all, allowing the sand to pass because it's too close to the recall cue. In the fourth case, it was Christmas tree. In the fifth case, a ship's wheel, what the captain cranks to move or turn the ship. And finally then, a gun. Look at, and if you take my picture off the screen for a minute, look at the recall on the second group, same time, different recall cue. Now, the two circles with a line are cued by the word dumbbell, the kind of thing that we use to, lift and build arm strength. Look at what happens to the drawing. And that's typical. It's not an extreme. That's a typical example of the drawings that were gotten. The number 8. A picnic table. End view of a picnic table. A mason's trowel. The sun. Bright. And a pitchfork. Look at the difference in drawings that you get. And in essence, what he demonstrated there back in the early 1930s is that memory is malleable. that it is essentially a reconstructive process. And what is argued there is basically that the recall cue that you use has a very direct impact on what you actually recall. Very powerfully. Much to his disappointment, his work basically was not honored, the value of it was simply not recognized for a long time after this work was published. But if we look at a comparison between the SR approaches that were used in the 1930s, 40s, 50s, and 60s, and compare that to our use of schemas, you get some very interesting comparisons. The first is the difference between what is called an atomistic as opposed to a molar approach. The SR theories are very nitty-gritty. Stimulus leads to response, what's the reaction time, and so forth and so on. They're based on very small units of knowledge and tied to the stimulus. Okay? The schema theories, on the other hand, are molar. They're holistically oriented. You'll remember the classic demonstration of two glasses with equal amounts of water where you pour one into a narrower, taller container. It's action-oriented, and it's much more integrated at the level of knowledge, which is organized into clusters of knowledge, how to act with water in a variety of ways. A second difference is essentially associationistic approaches as opposed to what can best be called non-associationist. Knew I'd have trouble with that word. I wish I'd never invented it, but I couldn't think of another word to describe it. The point is that the SR theories are based on learning simply as an association between any stimulus and its associated response. It's literally an SR, stimulus-response connection. By contrast, the schema theory is looking at knowledge as a structure for interpreting and encoding parts of a specific experience. So the link there, if there is a specific one, is between knowledge and what's been stored as opposed to the experiential situation where you're going to actually apply it. So it's a much broader link. Maybe there's an association or a link in that form, but it's so much more sophisticated in terms of the complexity of what's stored and how it can be applied. Very different kind of model using the schema. Thirdly, the SR approach can be described as essentially a particularistic. Okay? The SR theories are based on associations between a specific stimulus and a specific response. They then had to develop, you'll remember, even the concept of something like habit-family hierarchy to understand how one organism, in terms of the cognitive knowledge he stored, can respond so differently in different situations. They ended up needing to create something like a habit-family hierarchy. But the whole model is based on a specific link between stimulus and response. The schema theories, on the other hand, are much more general, showing a variety of particular instances, kind of like a protocol, and it's the culmination of particular instances in a given category of experiences. So they kind of draw the lessons out of a variety of individual experiences to reach the more general knowledge. A final difference is essentially that these theories are, the SR theories are passive as opposed to active. That is, in the SR theories, the SR link can be learned passively. Implicit learning, incidental learning. Whereas in the schema theory, it's an active process in which an experience is actively matched to the schema that best summarizes the experience for the participant. Okay? Those are four major differences between the more traditional behavioristic approach as to the modern schema-based analysis. It was 40 years between Bartlett's presentation and publication of his work and Beth Loftus's recognition of the relevance of it. You will remember the very magnificent study of eyewitness testimony she did in 1974, where the image that people tend to create when they're asked a question of speed, about how fast the cars were going when they smashed into each other, which is the most violent verb that she used in that question, versus the very neutral image when the question was, how fast were the cars going when they contacted each other. Just that verb creates a different image in the mind of the subject. And a week later, you'll remember, very compellingly, the violent verbs created many more false positives when the subjects were asked, was there any broken glass present? In that film, there was not broken glass. Cracked, yes, but it was not broken. And yet, if you have an image of a violent wreck precipitated by that verb a week earlier, when you then recall that information, you tend to image things, you build into that memory certain things that are simply not true, forced there by the logic of, if they smashed, there has to have been broken glass. But it was, as I said, it was many years. In fact, Bartlett was no longer alive by the time Loftus's work was published, and thus never came to realize that his work did ultimately have a significant impact on how we study modern day theories of memory storage. And so finally then, if we look at the various modern day theories, the question that we have is a rather interesting one. That is, modern theories basically come from contributions from two different areas. One of them has to do with AI programs, artificial intelligence programs, trying to mimic our work. And the other has to do with knowledge in cognitive psych, okay? Specifically what's been accumulated in the various research labs around the world. AI work is aided in detailing how schema-based organizations are achieved. And I'll leave you with a homework assignment that we'll review very quickly at the end of the next, at the beginning of the next tape. And that is, what kind of information would you want to have before registering for a particular course? What kind of information do you want before you sign up for any particular course? That's going to show you an example of an AI approach to the retrieval of information.